Okay, Chapter 1, Section 7, Solving Other Types of Equations. So in this section, we're going to look at polynomial equations, equations involving radicals, equations of a quadratic type, and then some applications or word problems. Okay, so polynomial equations. Some equations can be solved by factoring and using the zero product property, which says that if a product equals to 0, then at least one of the factors must be 0. So if you recall, we've already ran into that. It states that if we know two quantities, A times B equals to 0, we know for a fact that either the A is 0 or maybe the B is 0. So this works great if you can if you start with a multiplication, or if you can rewrite your question into the form of a multiplication equal to 0, then you can separate it this way. So let's look at some examples like that. For example, let's say that you're asked to solve this. So we have x to the fifth power equals to 9x to the third power. Do not make the mistake. One common mistake is that people just divide the x's. So if we have 9x to the third power, they think, okay, let me divide x to the third power, x to the third power. So I end up with x squared equals to 9. So x equals to plus or minus root 9. So x equals to plus or minus 3. Okay, do not do this. We don't want to do this because we don't know what x is. So it's possible x might be a 0. You know, what if x equals to 0, right? Then you're dividing by 0. So you don't really want to do that. Don't do it that way. Okay, so instead what we want to do is the following. Let's take x to the fifth power equals to 9x to the third power. And what we want to do is subtract both sides of the equal sign by this quantity or that quantity. Either way, you want to get it equal to 0. So minus 9x to the third power minus 9x to the third power. So that gets me to x to the fifth power minus 9x to the third power equals 0. And now what we want to do is factor out the common terms so that we can rewrite this subtraction into a multiplication and then use the zero product property. So both terms share x to the third power. So I'm going to factor out an x to the third power, giving me an x to the second power minus 9, which equals to 0. And then I can use the zero product property right here. We have this times this, so I can separate them. Oh, actually, in fact, I can factor this even further, right? This is a difference of squares. So this factors as x cubed times x plus 3x minus 3 equal to 0. And now we have a multiplication of 1, 2, 3 different things. And so by the zero product principle, either this guy, x to the third, is equal to 0, or the middle one, x plus 3 equals 0, or the x minus 3 equals to 0. Okay, so now from here, I get an answer of x equals to 0. I take the cube root of both sides. The cube root of 0 is 0. And then here I subtract minus 3 minus 3. That's going to lead me to x equals to negative 3 as one solution. And then over here we get a plus 3 on both sides. Plus 3, plus 3. So we get x equals to 3. X equals to 3. Okay, so we have 3 solutions. 1, 2, 3. And we can check them real quick. Check. And blank to the fifth power equals to 9 times blank to the third power. Well, the first one's really easy because if we replace x with a 0 there and a 0 there, 0 to the fifth power is 0. And 0 to the third power is 0. 0 times 9 is 0. So we do get a true statement when x equals to 0. When x equals to positive 3, we get this and we get that. X to the third power, 3 to the fifth power, and well, we could just get a calculator and confirm that these two work out. But also, if you notice, the 9 is actually equal to 3 to the power of 2. So it's really 3 to the power of 2 power of 3 equals blank to the power of 5. I'm putting these guys here, 3 there, 3 there. And let me just color match it and put this as a 9 right in there. Okay, so 9 is really 3 to the second power. So when I multiply these, I really have 3 to the fifth power, 3 to the fifth power. It all works out. So it is true, and the exact same thing is going to happen with negative 3. So all 3 are valid solutions. Okay, so move everything to one side, set equal to 0, factor, and if we can factor it and nicely and get to a point where we have a multiplication of polynomials that equal to 0, then we can use the zero product principle to simplify them. Here's your author's solution for this same question, and they did the same thing I did. Okay, good. Moving on. Okay, how about if we had to do factor by grouping? So remember that back when we were looking at factoring techniques, number 1 was factor any common numbers or letters that are shared by all the terms. And in this case, none of them are shared by there's no numbers that are shared by all 4. There are no letters that are shared by all 4. So there's no way to factor a constant from any of them or a common variable. Technique number 2 is to factor by grouping. And this one is a good candidate because there are 4 different terms, and that's what we needed for factor by grouping. Okay, so just like in the previous example, we cannot use the zero product principle because we have a bunch of additions and subtractions. If we can factor it and rewrite it as a multiplication of 2 polynomials, then we can use the zero product principle. Okay, so factor by grouping. Let's come over here. I'm going to put x to the third power plus 3x squared minus 4x minus 12 equal to 0. Okay, factor by grouping. Remember, I underlined the first 2 terms. Ignore the rest for a minute. Factor out whatever I can from those 2 terms, which is just going to be an x squared in this case. X squared, then we have an x plus 3. Right? Confirm that if I distribute x squared times x, I get x cubed. X squared times 3, I get plus 3x squared. Then plus blank and copy this binomial. Still don't pay attention to that yet. So then we copy x plus 3. And then we finally pay attention to the last 2 terms. So we want to fill in this blank right here such that when I distribute, when I multiply whatever this blank is times x, I get this first term, negative 4x, and blank times positive 3 equals to negative 4. A little bit of guessing and checking, and I think it's easy to see that this must be a negative 4. Right? Negative 4 times x is negative 4x. Negative 4 times positive 3 gives you negative 12. So that's what works out. Keep the equal 0 there. And then finally, we want to identify that we have a common binomial here. X plus 3, we're going to factor that out. So let's pull that out. We end up with an x plus 3, parentheses. And then what survives is an x squared from there and a plus minus 4 from there equals 0. Right, where I brought this x squared in there and this minus 4 from there. So it's the reverse of distribution, right? If I took this and distributed it across this polynomial, we would get this one. So I'm factoring it out. Okay, hopefully that sounds familiar. Okay, let me get rid of these colors. Okay, so now let's rewrite this guy as a subtraction of 4, and then we notice that that's a difference of squares. So if we have x plus 3 times x squared minus 4 equal to 0, then this becomes x plus 3 times x minus 2 times x plus 2, right? Realizing that this is 2 squared. 2 squared, so this is a difference of squares, right? In fact, let me just copy it on here. So 4 is really 2 squared, and so this is a difference of squares, and so we know from our section on factoring that this breaks up this way. And so now we have a multiplication of three binomials. 1, 2, 3 binomials. Everything's being multiplied. The answer is 0. So now we can take advantage of the zero product principle, which states that each one of these have a chance of being 0. So either the x plus 3 is 0, x plus 3 equals to 0, which means x equals to negative 3 is one solution, or the x minus 2 equals 0, which means x equals to 2 is another solution, or finally the x plus 2 equals to 0, which means that x equals to minus 2 is a solution. Okay, again, we can check this. Check. So this would be blank to the third power plus 3x squared. Oops. 3 blank squared minus 4 blank minus 12. Better be 0. And so we're hoping that these guys are going to be the correct answers. Let's start with negative 3. Negative 3, negative 3, negative 3. If we simplify that, we end up with negative 27. That's going to be positive 9 plus 3 times 3 makes it positive 27. So those will cancel. And then this becomes plus 12 minus 12. That works out. That's going to be 0. These two cancel. These two cancel. This equals 0. So that would be a solution. Okay. On the other hand, if we let the variable be 2 there, 2 there, 2 there, then 2 to the third power is 8 plus 2 to the second power is 4 times 3 makes it 12 minus 8 minus 12 equals to 0. Yes, these two cancel, also a true statement. Finally, let's check if negative 2 works. Negative 2 there, negative 2 there, negative 2 there. If we simplify it, we get negative 8. Negative 2 squared is positive 4. That makes it a plus 12. Negative times a negative makes it a plus 8. And then a minus 12. And yes, again, it works out. So all three solutions work out. Here's your author's solution for this question.
Okay, so let's cover a few other variations. Let's say that we wanted to solve this equation. Okay, so what we want to do with something like this is to start off by factoring everything. And the only thing that really needs to be factored is this guy. So I'm just going to rewrite the whole thing. 3 over x minus 2 over x minus 3 equals negative 12. And the way it factors is we have x squared minus 9. That's x squared minus 3 squared. And so we have a difference of squares. So this factors as x plus 3 times x minus 3. Okay, so that's going to become x plus 3x minus 3. What we want to do is find the LCD of all the denominators, and that's going to be as follows. LCD, the least common denominator. Well, there's a copy of x, there's a copy of x minus 3, and also a copy of x plus 3. And so using one of each of those, we'll be able to get the least common denominator. Okay, so I'm going to copy it here. 3 over x minus 2 over x minus 3 equals to negative 12 divided by x plus 3, x minus 3. And now I'm going to multiply this side by x times x minus 3 times x plus 3. I'm going to multiply this side by the exact same amount. X times x minus 3 times x plus 3. As long as I'm doing the same thing to both sides, I've maintained that equality. So I have to multiply all of it, right? I multiplied everything on the right-hand side by this amount, so I have to multiply everything on the left-hand side by the same amount. So I have to distribute. I'll end up with x times x minus 3 times x plus 3 times 3 over x minus, and then another, once I distribute, I get x minus 3, x plus 3 times, and I'll get a 2 over x minus 3 equals the right-hand side, which is negative 12 over x plus 3, x minus 3 times this, which is x minus 3, x plus 3. Good. So now a bunch of stuff will reduce. This x reduces with that one, and then this one reduces with that one, and then both of these cancel with both of those. So after all that cancellation, what remains is this product times a 3, so I'll get a 3 times x minus 3 times x plus 3, and then minus x times x plus 3 times 2 equals to negative 12 times x. Okay, so we're going to have to do a little bit of foiling here. So foil this guy, foil, 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 and distribute. And don't forget that this guy applies. So distribute, and also distribute and distribute. So after I FOIL, I'll get 3 parentheses. This will be x squared minus plus 3x plus 3x minus 3x minus 9. Right? The middle terms will cancel. And then we keep going. This will become a minus x squared minus 2x squared, and then minus 6x equals to negative 12x. Again, continuing to distribute this 3, we end up with 3x squared minus 27 minus 2x squared minus 6x. And I'm going to go ahead and bring this over to this side, so I'll end up with a plus 12x equals 0. And then combining like terms, I'll end up with just one copy of x squared. That's combining this guy and this guy. That just gives me one copy of x squared. Then combining these two, I get a plus 6x minus 27 equals 0. So if I can think of two numbers that multiply to negative 27 but add to positive 6, how about x plus 9, x minus 3, multiply to negative 27 but add to positive 6 equals 0. Now by the zero product property, I know that this must mean that either x plus 9 equals to 0 or x minus 3 equals to 0. So we get two answers. Either x equals to negative 9, that's one solution, or x equals to positive 3 is another solution. Okay, so let's go back to the original statement. The original statement was this guy right here. So if we can come back and replace the x by those values, we can determine if we have a true statement. So we have 3 over x 3 over x, and then it was minus 2 over x minus 3, and then negative 12 equals to negative 12 over x squared minus 9. Right? X squared minus 9. Okay, so Okay, so we can check to see if in fact this is true. So it's 3 over blank minus 2 over blank minus 3 equals to negative 12 over blank squared minus 9. So let's check with a negative 9. So let's put a minus 9 there, and a minus 9 there, and a minus 9 there, and see if in fact we get a true statement. So that's going to reduce to negative 1/3, and that's going to be minus 2 over, that's going to be negative 12, and hopefully that's equal to negative 12 divided by 81 minus 9, (72), and then that'll reduce. So then that'll reduce, we have 8 and 9. So multiply this guy by 4 over 4. I'll end up with minus 4 over 12 plus 2 over 12. So on the left-hand side, I'll end up with negative 2 over 12. On the right-hand side, this will reduce. The 12 times 6, that's going to be equal to 1 over 6. So this is going to be equal to negative, this is equal to negative 1 over 6. Right? 12 times 6 is 72. And then this reduces to negative 1 over 6. And so this will reduce to exactly that, right? So this is true. Okay, and then what about the other one? If we focus on the other one, we've established that this one's a true one. But what about the other one? So we have 3 over blank minus 2 over blank minus 3 equals to negative 12 over blank squared minus 9. And so here we have a 3 that's going to reduce to 1. And here we're going to have a 3 that reduces to 0. Here we're going to have a 3 that's going to reduce to 0. And both of these cause a problem because we're going to end up with a 0 in the denominator. Right? So these guys reduce to 1 minus 2 over 0 is equal to negative 12 over 0. And remember that that means that these are undefined. Undefined, right? So it's not valid. That means that this is not a valid solution. So the only solution here is x equals to negative 9. Multiplied both sides by this. Good. Reduced. We got to that. Distribute. Combine like terms. We end up with this. Factors into that. We got the 3 and the negative 9. And then if we plug it into our equations, we see that the 3 causes a problem. We get undefined. And that the negative 9 works out well. So both of them give you a true statement. Okay, so negative 9 is the only solution. All right, what about something like this? Let's start off by simplifying this a little bit. Let's get rid of this root first, because otherwise, we can't solve for x. There's an x inside the root and the argument of the root. So let's get rid of it. And to do that, I'm going to isolate it first and then square both sides. So the first thing I'm going to do is move things around a little bit. So I'm going to rewrite this in the following way. I'm just going to move this over to this side. So I'll end up with positive root 2 minus x. And I'll move this to the other side. That equals to 1 minus 2x. Right? Moving that over there. and then moving this over here. And now that I've done that, I'm going to square both sides. Minus x equals to 1 minus 2x. So I'm going to square this side, and then I'm going to square this side, giving me just a 2 minus x is equal to this guy squared, which becomes 1 minus 2x. I'm going to FOIL it all out. 1 minus 2x, which gives you 2 minus x is equal to, FOILing it out, we get 1 minus 2x minus another 2x plus 4x squared plus 4x squared. And now I'm going to set everything to one side, set it equal to 0, and combine like terms. So we get 2 minus x is equal to 1 minus 4x plus 4x squared. And then if I move this over to this side, I have to add plus x, and then minus 2 and minus 2. So I'll get 0 equals to negative 1 minus 3x plus 4x squared. If I now just move those things around a little bit, I'll get a 4x squared minus 3x minus 1 over here. 0. So I'll just flip it around a little bit and say it's 4x squared minus 3x minus 1 equals 0. So now let's factor that guy. I think because the numbers are so easy, we can just kind of use the guess and check method. It's going to be something that fits this form. Blank x plus blank equals 0. So we can just kind of guess and check different things. Because it ends in a 1, I know that the last term has to be a 1. So this is plus or minus something here, plus or minus something there. It seems like a pretty good bet that these guys are going to be 1s. And so now the first two terms have to multiply to this one. So 4, it could only be 2 and 2. So we can try 2 and 2, see if that works out. Play around with it. I get a 4, then I get a 2, and then either a minus 2 plus 2. That's not gonna work out. So let's try something else. The only other thing it could be is a 4. So let's try putting something like 4 and 1, and then playing around with it a little bit. So that'll give me my positive 4, and then that'll give me like a plus 4 or a minus 4, and then this will give me a plus 1 or a minus 1, depending on whether I choose plus or minus, and that seems to work. 4 and a 1, that can lead me to a negative 3. So again, just by guessing and checking different things, I think that the one that will work is going to be 4x plus 1 and then x minus 1. It's just a guess, so let's check it. That'll be 4x minus 4x, 4x squared minus 4x plus x. That'll give me that minus 3x and then minus 1. Good. So guessing and checking worked, because the numbers are so easy. But if not, we can also use the quadratic formula, right? So we can just go over to a equals to 4, a equals to 4, b equals to negative 3, c equals to negative 1. And then we can use the quadratic formula, x equals to negative b plus or minus the square root of b squared minus 4ac all over 2a. And then that will lead to our answer as well. But here, this isn't so bad. So then we can separate this into either that's equal to 0, which leads to 4x equals to negative 1, which means x equals to negative 1/4 is one solution. Or the other solution is x minus 1 equals 0, therefore x equals to 1 is the other solution. And remember, we got to check them. So we got to come back over here and determine if it's in fact true that these guys give us our answers. The easiest one to check is 1. So let's come back over here, plug a 1 for each one of those, and see if it in fact gives us the right answer. So let's put a check over here. Check. And we had 2x equals 1 minus the square root of 2 minus x. So let's see if 1 is in fact a valid solution. Right, here are my two solutions. So check if x equals to 1 is an answer. I'll have 2 times something is equal to 1 minus the square root of 2 minus something. If I put a 1 there and I put a 1 there, I get on the left-hand side a 2, right? These guys multiply to 2, equals 1 minus, and this will become 2 minus 1. That'll be root 1. Root 1 is just 1, so I get 2 equals to 1 minus 1, which is then going to be equal to 0, right? So this fails. I get a 2 equals to 0. That's a fail, right? Which means that this is not really a valid solution. All right, let's check the other one. The other one is going to be this. We get that 2 times blank is equal to 1 minus the square root of 2 minus blank. And I'm going to check to see if, in fact, it's negative 1/4. Negative 1/4 goes there. Negative 1/4 goes there. And see what we get. So this will reduce to negative 1/2 on the left-hand side is equal to 1 minus. That's going to be 2 minus minus. That's going to be plus. As a mixed number, let's do that. As a mixed number, it's going to be 2 plus 1/4, so 2 and 1/4 as a mixed number, which means that to convert it into a fraction, it's going to be 9 over 4. Negative 1/2 is equal to 1 minus the square root of 9 over 4. Or we could have gotten the common denominator, 4 over 4, that's 8 plus 1 over 4, that's 9 over 4, which then reduces. We get negative 1/2 is equal to 1 minus 3 halves. And 1 minus 3 halves, that is going to be true. Negative 1/2 is equal to negative 1/2. Right? 3 halves is 1.5 as a mixed number, so 1 minus 1.5 gives you negative 1/2. Great. So this one works out. This one works out. So this is the only true solution. X equals to negative 1/4. Okay, so when you run into situations where you have an equation and there happens to be a square root somewhere in there, one way to do it is to leave it alone, keep it together as a little unit, isolate it, and then you can square both sides so that so you can get rid of the root and then move forward, try and solve it. The only thing is you have to be real careful to check your solutions because you might have sort of a phantom answer that results from the fact that you square both sides. Remember that when we square both sides, we run the danger of potentially making something that isn't true become true by the fact that we square both sides. So if at this stage, maybe this is equal to negative 5 and this is equal to positive 5, I square both sides, then I get 25 equals 25. I'll get a true statement after that. Okay, so that's why you have to check your solutions to see, to confirm that they work out. Okay, so let's see what the author did. Hopefully something similar. Looks like the author did something similar. Moved the 1 over, squared both sides. You get this, move everything into equal to 0, factored it, checked both of them. So the negative 1/4 works out. Both give you negative 1/2. And the 1, x equals to 1, does not work out. So when we solve equations, we may end up with one or more extraneous solutions, right? These are these phantom solutions that occur that don't actually solve the satisfy the original statement. Extraneous solutions may be introduced when we square each side of an equation because the operation of squaring can turn a false statement into a true one. So if we started out with something that was false, like negative 1 equals to 1, but we squared both sides, we would end up with 1 equals 1, and that is true. So we can start off with something false, square both sides, and end up with something that's true. That's why we have to be careful. Okay, almost done. Last example. What if we had something like this? I like to call these quadratics in disguise. Remember, this entire section, for the most part, or a large part of this section has been really been focused on quadratics, right? Things that can be solved that fit this form. Ax squared plus bx plus c equals to 0, right? And so a power 2, that's a quadratic. We know a lot about this stuff. We can factor it. We can use the quadratic formula. And so this one here doesn't initially look like it fits that form because it's a power 4 instead of a power 2. But if we do a very straightforward substitution, like say a u substitution, why don't we let u equal to x squared, then that must mean that we can rewrite this as x squared squared, right? That's x to the 4th power, minus 8x squared plus 8 equals to 0. And now I can do this substitution where I let u equal to x squared, and I get u squared minus 8 times u plus 8 equals 0. And now I have a quadratic in disguise. This is going to fit this form. Fits with A, the role of A being played by a 1, that's a 1 in front, the role of B being played by a -8, and the role of C being played by an 8. So now I can use the quadratic formula. Now over here, by default, we use x a lot. So the variable here is x, so I just switched my variable to u. So now I'm saying that the solution to this is going to be equal to u, and it's that little formula. Negative b plus or minus the square root of b squared minus 4ac all over 2a. Quadratic formula. So therefore my u is equal to -1 times b, where the b is a -8. So I'll have this -8, -8, plus or minus the square root of -8 squared minus 4 times 1 times 8 all over 2 times a, which is a 1. Okay, so be careful that the b, this b has its own sign to begin with. The formula has a negative, but then the b came with its own symbol. So that's why there's 2 here. There's that sign that it came with, and there's another one, meaning that the u is actually going to be positive. So I'll get that u is equal to 8 plus or minus the square root of, and then -8 squared gives you a 64, and then 4 times 8 is 32. All of that gets divided by a 2. So let's put this up here. So that means that my u is really going to be equal to 8 over 2 plus or minus square root of 32 over 2. And we can factor this out. This simplifies. U equals to 4 plus or minus. Now the 32, stick it right in here, 32 is really equal to 2 times 16, and it's equal to 2 times 8, and it's equal to 2 times 4, and it's equal to 2 times 2. So 32 is really equal to 2 to the power of 5. So there's an invisible little 2 here. We can pull them out in groups of 2, and so we can pull out several of these, right? We can pull out a 4. So this is the same thing as saying that it's square root of 16 times 2, or 2 over 2, which means that my u is equal to 4 plus or minus 4 square root of 2 over 2. And pulling out that 4 is the same thing as pulling out little groups of 2 in powers of 2. Right? So that's the other thing I was pointing out, right? That this guy, we can think of it as root 32 is the same thing as root 2 to the power of 5, which is equal to 2, and then 2 to the power of 2 times 2 to the power of 2 times 2 to the power of 1. And now this turns into 1 copy of 2. Square root of 2 squared, this turns into 1 copy of 2 out there. And then this one turns into another copy of 2 outside the root. And then we still have 1 copy of root 2 inside the 2. And so we end up with 4 root 2. Any way you want to think about it, either way. Or you can separate the 32 into 16 times 2. And so the square root of 16 is 4, and that reduces. Finally, back out here, this 2 will reduce with that one, giving me a 2. And we end up with u equals, so my u then equals 4 plus or minus 2 root 2. And we're almost done, except that the original question was not about u. The original question was about x to the 4th power minus all that. I'm the one that did this substitution, so we can't be done yet. We're going to have to come back and replace this here as well. So I'm going to bring this guy over and substitute it right in there. So remembering that u was actually defined to be this, that's how I did all of this. I end up with x squared is equal to 4 plus or minus 2 root 2. And so now when I solve for x, I'll end up with x equals to well, let's take the square root of both sides. So I'm going to take the square root of this side and then the square root of that side, keeping in mind that I have to throw in the plus and minus. So it'll be plus or minus square root of 4 plus or minus 2 root 2. That's ugly. Let me zoom out a little bit. So we have several options here. This leads to several possibilities. So first of all, the outer layer of plus or minus leads to 2 possible answers. So I get x equals 2 root 4 plus or minus 2 root 2. Okay, that's one route. The other route is that x equals to negative root 4 plus or minus 2 root 2. And then each one of these lead to 2 possible answers. Either x equals to the square root of 4 plus 2 root 2, or x equals to the square root of 4 minus 2 root 2. Or this one leads to 2 possible answers. X equals to negative root 4 plus 2 root 2. Or x equals to negative root 4 minus 2 root 2. Okay, so we end up with 4 possible answers. We have this one, we have this one, we have this one, and we have that one. We can leave it alone like that, or we can convert each one of those into a decimal approximation. And then, of course, in order to check to make sure that all of them work, we'd have to come back over here, plug them in for x, and figure out if they are actually going to give you a true statement. Let's see what the author did for this. So he did a W substitution instead of a U substitution. So substitute it there. We end up with quadratic formula. We get the same answer here, plus or minus 4 root 2 over 2. Okay, so you get 4 possible answers, and then you can use your calculator to get a decimal approximation for them. Here they are. And then you should actually test them one at a time to really see if they really do give you the right answer. Okay, so that should be enough to get started on your homework in 1.5. Let me know if you have any questions.
Okay, now let's tackle a question like this one. Solve this equation. 1 plus 1 over x parentheses squared minus 6 times 1 plus 1 over x plus 8 equals to 0. So the first thought, my first temptation, I would say, is to maybe FOIL this out, right? And then if you FOIL it all out and then distribute this 6 and then you combine like terms and then you cross your fingers that something cool happens. But another thing that pops out is that this is identical to this. So that's kind of curious. And it's this in yellow raised to the power of 2, and then this in yellow raised to the power of 1. So because it happens to be an equation that fits that sort of form, I could see that this is an example of a quadratic in disguise. It's something squared minus something to the same power, right? Like if I had a letter here, this was like a giant W, W squared minus 6 times W plus 8, and then that would just be a quadratic. So that's the strategy we're going to use here. We're going to look for things that look like they're quadratics in disguise and simplify them. So I'm going to do a substitution. I'm going to let W, now W is just an arbitrary letter, but you could choose whatever letter you like other than X, because otherwise that'll look confusing. So let W equal to 1 plus 1 over X, and now I'm going to replace each of those values with W. So I'll end up with W here and a W over there, and then it'll be W squared minus 6 copies of W. Well, that's kind of too far away. Of W plus 8 equals to 0. Okay, so now that's a quadratic in disguise there. We can simplify that, get an answer for W, and then once we have a value for W, we can go back over here, replace W with the value of 1 plus 1 over X, and solve for the indicated value, which was actually X. Okay, so to factor this, luckily this is an easy one. This is a trinomial in the letter W. The leading coefficient is a 1, so this is hopefully going to work out nicely as something that factors out like this. So W times W gives you W squared. We're looking for two numbers that multiply to 8 but add the negative 6. So that's just going to be 4 and 2 multiply to 8. And now I need negative 6, I need positive 8. So if they're both negatives, that works out. Negative 4 times negative 2 gives you positive 8. And negative 4 plus negative 2 gives you a minus 6. So that works out. Now we have the zero product principle. Two binomials being multiplied, the answer is equal to 0. That guarantees that at least one of them must be 0. So W minus 4 is equal to 0 is one solution, or W minus 2 equals to 0 is another solution. Bringing the minus 2 over, we get that W equals to 4 is one solution. And then bringing a 2 over, we get that W equals to 2 is another solution. And just when you think you're done, that's when you got to come back over here and replace the W with the 1 plus 1 over X. So now we're going to come over here and rewrite this as 1 plus 1 over X must be 4. And now we have to solve for X in this one. So I'm going to subtract 1 from both sides. Minus 1 minus 1. And I end up with 1 over X is equal to positive 3. And then I'm going to multiply both sides by 3. Multiply both sides by X, times X times X. We end up with 1 equal to 3X. And finally multiply both sides by 1/3. 1/3, 1/3. And we arrive at our answer. X equals to positive 1/3. I'm going to flip it around and write this as X equals to 1/3. Okay, so that's one solution. Now we got to work out the other one. Again, we replace the W with a 1 plus 1 over x equal to 2. Subtract 1 from both sides. Minus 1, minus 1. And so we end up with 1 over x equals to positive 1. And so now when we multiply both sides by x, we'll get to our answer. Times x, and so x equals to 1 is the other solution. Okay, so to check it, I'm going to come back over here. Check. 1 plus 1 over blank, parentheses squared, minus 6 times 1 plus 1 over blank, plus 8. Hopefully that whole crazy thing equals to 0. Let's start with the easy one. So we're going to check if in fact 1 gives us a true statement. Put a 1 there, put a 1 there. Okay, 1 over 1, that's just 1. Plus 1, that's 2. So this will simplify into just a 2 squared minus 6 times 2 plus 8. Hopefully that equals to 0. That gives me a 4. 4 minus 12 plus 8 equals 0. Yes, it does. 4 minus 12 is negative 8 plus 8 gives you 0. So it worked out with the positive 1. So let's go ahead and box that up as an answer. What about this one? X equals to 1/3. Is that an answer? Okay, so if we replace the x with 1/3 into this little format, we end up with 1 plus 1 over 1/3. Put a 1/3 there. All right, so this simplifies. We have the numerator being a 1, and then we have a little fraction in the denominator. We multiply the numerator times the reciprocal of the denominator. This is just going to be 3. So this becomes 1 plus 3, parentheses squared, minus 6 times 1 plus 3 plus 8. This becomes 4 squared, minus 6 times 4 plus 8. That gives you 16 minus 24 plus 8. Does that equal 0? Yes, that's a minus 8 plus 8 does equal 0. Okay, so both were valid solutions. All right, let's try one more quadratic in disguise. This one's extra tricky. It's really hard to notice it. Just takes a little bit of practice, but it is really tough to spot. And if you've never seen this before, it would be really, really hard to do. So what we want to do is manipulate this to make it fit a quadratic. So we need something squared and another term. So I need one of these to be squared. Remember our power rules that if I have x to the power of 2 times x to the power of 3, if we're multiplying two exponential numbers with the same base, we add the exponents. So this equals to x to the 5th power. On the other hand, if we have an exponential number and we raise that to the power of 2, then we multiply them. This becomes x to the power of 3 times 2, which gives you x to the power of 6. So this is the property I want to take advantage of. I want to rewrite this fraction this way. I'm going to scoot it over here, have some room. X to the 1/3 power plus x to the 1/6 power minus 2 equals to 0. Okay, so what I'm going to do is I'm going to focus on these little exponent guys, and I'm going to notice that if I want a common denominator, I can rewrite the 1/3 this way. I can write x to the 1/3 power. I can multiply this by a little 2 over a 2 right in there to give me a 2 over 6 from here, plus a x to the 1/6 minus 2 equals to 0, right? So 2 over 6, that reduces to 1/3. But I did that because now they both have a 6 in the denominator of this little fraction. And now I can also rewrite it this way. X to the 1/6 power raised to the power of 2 is the same thing as that. Remember our little property, if we have an exponential number raised to another power, we multiply them. And 1/6 times 2 equals to 2 over 6. So that gives me a way of rewriting this as a quadratic. Good. So now we're going to let w be this value, right? So now if I Focus on this green guy and this guy. They're identical. So if I let them be w, I get w squared plus w minus 2. Right, so let's do a substitution. Let's let w equal to x to the power of 1/6. So we end up with w squared plus w minus 2 equals 0. Now this is a simple trinomial in the letter w. Leading coefficient is a 1, so hopefully this will factor as w times something plus something times w times this guy like this. Okay, two numbers that multiply to -2 but add to 1. Well, that should be a 2 and a 1. And let's make this a plus because we need a plus 1 and a minus. So w plus 2, w minus 1 are the two terms that give you this. By the zero product property, that means that I can break these down. So w plus 2 must be 0, or w equals to minus 1 is minus 2 is one solution. And w minus 1 equals to 0, which means that w equals to positive 1 is another solution. Okay, just when you think you're done, you got to come back over here and replace your variable. So let's come down here. So now we replace x to the power of 1/6 is equal to -2, and x to the power of 1/6 equals to positive 1. To simplify this, we got to raise both sides to the power of 6. So -2 raised to the power of 6 is going to be equal to positive 64. And on the other side, we also raise both sides to the power of 6, and so we end up with x equal to 1 as an other solution. Okay, so now let's check these. To check these, we got to go back to our original statement. Okay, so going back to our original statement, blank to the power of 1/3 plus blank to the power of 1/6 minus 2 should be a 0. Let's start with the easy one first. Does 1 give us a true statement? Putting a 1 there, putting a 1 there. Is this true? Well, remember that 1 to the 1/3 power is the same thing as the cube root of 1 plus the 6th root of 1 minus 2. Does that equal 0? The cube root of 1 is 1 plus the 6th root of 1 is also 1. Minus 2 does in fact give you 0. That's a true statement. Let's look at the other one. Blank to the 1/3 power plus blank to the 1/6 power minus 2 equals 0. Okay, does a 64 give us a true statement? Putting a 64 there, putting a 64 there. Okay, so now this is the same thing as the cube root of 64 plus the 6th root of 64 minus 2. Does that give me a 0? Well, no. This is going to be the 6th root of 64. Well, that's 2 because we already established that 2 to the power of 6 is 64 from over here. Minus 2, that's going to be 0, but then we have this, the cube root of 64, which is 4. 4 times 4 is 16, times 4 is 64. This leads to 4, so this does not equal to 0, right? So this one's not a solution. So the only solution we have is x equals to 1. Okay, applications. Let's look through a word problem. So a group of people come forward to claim a $1 million lottery jackpot, which the winners are to share equally. Okay, so first of all, jumps out at you, a group of people. So they don't tell us how many people, but they will share the $1 million jackpot equally. Before the jackpot is actually divided, 3 more winning ticket holders show up. Okay. As a result, the share of each of the original winners is reduced by $75,000. How many winners were in the original group? Okay, so we have 2 different groups we're dealing with. Group 1, the original group of people, right? A group of people We don't know how many, maybe 10, maybe 12, 6, 4, we don't know. A group of people were to win $1 million and share it evenly amongst all of them. I don't know. Let's say this just for the sake of thinking about this problem. Let's say that this group was 10. You're sharing this, and so you're going to get $100,000 each. Okay, but then 3 additional people come in. So now this would grow by 3 more. And when you grow by 3 more, they're letting us know that the share of the winning jackpot of the original people is reduced by 75,000. Okay, so let's figure out what the original group sizes were and what the original quantity that they were going to get was supposed to be. So let's translate this word problem, right? So whenever you run into a word problem, you got to read it a couple times, make sure that you have a good idea of what it's saying, what it wants you to find out, what is changing, what stays the same, and then start assigning variables. So we need a few variables. We need a variable for the original group of people, which we don't know. So let's organize it this way. So let x be the number of people in the original group. Like I had guessed, maybe 10. And so if it was 10, the $1 million would be divided amongst all 10. That would be 100,000 each. But that's just the number I made up. It could be anything. Maybe the original group was 3 people, 2 people. We don't know. So let x be the number of people in the original group. Since 3 additional people showed up, the number of winners in the final group is going to be x plus 3. Right? Don't assign extra letters. That's a common mistake. We assigned x to be the number of people in the first group, and it would be a mistake to just assign a new letter to the number of people in the final group, because we know the relationship between those two groups is simply to add 3. So don't add extra letters if you don't need to. So x plus 3 is the number of people in the final winning group, the number of people that win it. Okay, originally the $1 million was to be divided amongst the original group, the x. That's what gives you how much they were going to originally win. But then once we identified 3 additional winners, the $1 million is divided amongst the x plus 3, right? So this is the winnings per person. The final winnings per person is going to be 1 million divided by x plus 3. Okay, so now that we've organized all our information into these equations, also keep in mind the 75,000. So we know that the amount of money that the originals was going to win is decreased by 75,000. So the amount of money the originals were going to win minus 75,000 equals the amount of winnings per person that they finally ended up getting. Good. Okay, so the winnings per person originally, well, that's 1 million divided by x minus 75,000 equals to the final ones, and that's 1 million divided by x plus 3. Good. So this is, remember, don't lose track what the values of these variables mean. X represents the number of people that were original winners. So 1 million divided by x gives you an amount of money. This is how much each person was going to win originally. Good. And this is how much money each person ended up winning after the 3 additional people came forward. Okay, so now we have ourselves an equation. Okay, so now to solve this one, I'm going to point out that this fraction has an x in the denominator. This fraction has an x plus 3 in the denominator. So I'm going to multiply both sides of the equal sign by x times x plus 3, and that'll get rid of all our fractions. That's a good first step. So I'm going to multiply this whole thing. Let's put it on this side. I'm going to multiply this whole thing by x times x plus 3. Multiply this whole thing by x times x plus 3. Okay, then I'm going to distribute. So I'll end up with, I'm going to squeeze it over here, x times x plus 3 times 1 million over x minus x times x plus 3 times 75,000 equals this, which is 1 million divided by x plus 3 times x plus 3. Okay, so now a bunch of stuff will cancel. Here, this x will cancel with that x. Here, the x plus 3 cancels with that. And, well, nothing cancels here, but we don't have any fractions now. So we end up with, x plus 3 times 1 million minus, I'm going to go ahead and distribute this guy. We end up with x squared plus 3x times 75,000 equals to 1 million times x. 1, 2, 3 times x. Okay, these numbers are pretty big, so let's come up with a way of simplifying them. Let's come up with the biggest number that divides, well, there's not really 3 of them, there's only 2. There's 75,000 and there's 1 million. So the biggest number that divides 75,000 is 75,000, but that does not divide 1 million evenly. 50,000 does not divide 75,000. 25,000 divides it evenly. So 25,000 is the biggest number that goes into 75,000 and also goes into 1 million. So if I divide everything by 25,000, so this whole side by 25,000, or actually let me just do each one separately. Divide this by 25,000, divide this by 25,000, divide that by 25,000. Okay, so this reduces a little bit, a little more manageable. 4 times 25,000 gets you to 100,000. So we need 10 more, so this would be 40. So this will simplify to 40 times x plus 3 minus 3 times x squared plus 3x equals to 40x. All right, let's keep going to try and simplify. Now I'm going to distribute this 40, distribute this 3, combine like terms. And so I'll end up with 40x plus 120 minus 3x squared minus 9x. And moving this over, I get a minus 40x equals 0. So now already I can see some benefits. This minus 40 and this plus 40 minus 40, those guys reduce. And so I have these 3 terms remaining. So I'm going to move these around. I end up with a minus 3x squared minus 9x plus 120 equals to 0. I'm going to factor out this minus 3. Minus 3. I end up with x squared plus 3x minus 40 equals 0. Okay, and now we have a perfect square trinomial here. We're looking for 2 numbers that multiply to 40 but add to 3. So 5 and 8 come to mind. X plus 8, x minus 5. These 2 multiply to negative 40 but add to negative 3. There's still a minus 3 out there. There's still this 0. And so now the zero product property tells us that if we have these 2 binomials multiplying, the answer is 0, then I can separate this into 2 cases. X plus 8 equals to 0, which means x equals to minus 8 is one solution, and x minus 5 equals to 0. So x equals to 5 is another solution. Now remember what the value of x was. The value of x was the number of people in the original group that won the lottery. So we can't have a negative, right? We can't have a negative number of people in this group. It doesn't make sense. So we can automatically cancel out this guy, and this becomes our only potential solution. X equals to 5. So let's double check it and make sure that it all works out the way we want it to in accordance to this word problem. Okay, so after all that work, we saw that x was equal to 5. which means that there were 5 people in the original group of winners. And then after 3 people added to the group, that means that there was a total of 8 in the final group, which means that the original amount that they were going to win was going to be 1 million divided by 5. But then after 3 additional people showed up, it turns out that the final winnings was 1 million divided by 8. 1 million divided by 5 equals to 200,000. So they were originally going to win 200,000 when there were 5 winners. But then 3 people showed up. Then they had to split the 1 million amongst 8 people. And if we divide 1 million by 8, we get 125,000, which is the final winnings that they received. And we see that the gap between those is 75,000. They lost 75,000 as the word problem indicated. Okay, so they were originally going to be 5 winners. They each were going to get 200,000. After 3 people were added to the winning pile, then there was a total of 8 winners. And 1 million divided by 8 is 125,000, which is decreased by 75,000. Okay, so hopefully that's enough to help you finish your homework. As usual, come to my office hours if you have any questions.